In this chapter, we're going to talk about water and ocean structure, and really this chapter is quite a bit about ocean physics. So let's take a look at the water molecule. Here we go. The water molecule is made up of two atoms of hydrogen bonded with one atom of oxygen to make H2O. And because of the way atoms bond, in this case, they are sharing electrons to complete their outer shells. So hydrogen wants one more to complete its outer shell and have two electrons. And oxygen's outer shell has 6. It wants two more to have 8. And so that's why we bring in two hydrogens. And so you can see the final configuration right here. And what you'll notice is it looks very much like Mickey Mouse. So if you remember nothing else from this chapter, you could at least remember the shape of the water molecule is like Mickey Mouse. Now it turns out that this is important. You'll notice that our little Mickey Mouse shape here, the ears, because they're hydrogens and the hydrogens are sharing their electrons with the oxygen, their nuclei are exposed, and the nucleus has a positive 1 charge because it has 1 proton each in each of those nuclei. So we have +1 and +1, and that's kind of sticking out there with a positive charge. The chin of Mickey Mouse, you can see there's a whole bunch of the electrons from the oxygen's outer shell kind of clustered there, and so that gives the chin of the Mickey Mouse structure a negative charge. And so you can see the oxygen molecule, if we look at it up close, is what we call a polar molecule. It has a negative charge on one side and a positive charge on the other. This is going to give our water molecule some very interesting and important characteristics. The water molecules tend to stick to each other. You'll notice that the positively charged ears tend to point toward and stick to the negatively charged chins through these hydrogen bonds, and that means water likes to stick to itself. It means that water is cohesive. The water molecules stick to each other. This creates things like surface tension, and it will mean that it's a little more difficult. In fact, actually, it's a lot more difficult to get water to evaporate. It takes a lot of energy to pry these things apart and put a water molecule out into the air as a gas. So the water molecules like to stick to each other as liquid water. The second important characteristic is adhesion, and this will come up more in the next chapter when we talk about ocean chemistry. But the water molecules also like to stick to other substances. And in fact, not only do they stick to other substances, but we'll see that water has a tendency to be able to pull other substances apart. If the bonds aren't very strong, it can actually pull apart the bonds that hold other molecules together. A really good example is salt. So table salt, the stuff that you put on your food, is sodium chloride. It's a little solid crystal. If you dump that into water, the sodium chloride crystal is bonded together using what we call ionic bonds. It is the sodiums and the chlorides are attracted to each other because they have opposite charges. And it turns out that the water molecules can tug on those sodiums and chlorides and pull them apart and isolate them. And so that's what happens when sodium chloride dissolves. So what we're going to do is take a look at a few of the characteristics of water. The first thing we're going to look at, and we're going to spend some time on this, are the thermal characteristics of water. And the thermal characteristics of water refer to the heat properties of water. So first of all, heat is a measure of energy, and I highlighted that in red because that's important to remember. It's a measure of energy produced by the vibration of atoms and molecules. And it is measured in calories. There are some other terms you could use, but we're going to just stick to one. So we're going to measure the heat energy in calories. The temperature of an object is the object's response to the input or removal of energy. And so they mention heat, but really we could say any kind of energy. And the motion of the atoms and molecules is what the temperature is actually measuring. The faster those atoms or molecules are moving, the higher the temperature. The slower they're moving, the lower the temperature. And what heat is a measure of the total energy contained in those moving atoms and molecules. So if you have a lot of atoms and molecules moving very quickly, that's a lot of heat energy. If you have a few atoms and molecules, even if they're moving quickly, the temperature can still be high, but if you don't have a lot of them, if the total number is low, then the energy is low as well. And we're going to measure temperature, or this movement, in degrees centigrade or Fahrenheit. And actually in this class, we'll just focus on centigrade. Next term is heat capacity. The heat capacity is the energy added or released with temperature change. And we measure it in calories per gram per degree centigrade. So you'll see the term calories, which is a heat term, degrees centigrade, which is a temperature term, and gram, which is mass. So calories per gram per degrees centigrade. And it's basically how much energy, that's the calories, it takes to heat a gram or a certain mass of the substance a certain number of degrees centigrade. And typically the unit we use is the number of calories it takes to raise 1 gram of the substance 1 degree centigrade. The other term, you'll notice, also has heat in it, latent heat. And this is the energy that's added or released when we change state. So when we go from a solid to a liquid, or a liquid to a gas, energy is added or released with that change in state. Now, when we change state, the temperature doesn't change, all right? The energy in that case is being used to change the state from solid to liquid or liquid to gas. And so the temperature is stable while the state changes. And this is measured simply in calories per gram because, again, we're not changing the temperature. So let's take a look at how this works with water. This is a very busy slide. It's got some really important information on it. And then the next 2 slides will have some visuals so that we can discuss this and make some more sense of it. So, item number 1, bullet number 1, right up at the top here. Water can absorb, store, or release large amounts of energy with a small, or in the case of changing state, no change in temperature. Now this is really important. It means that the water is going to be able to absorb and store large quantities of energy. And this is going to be really important as we go into some of the next chapters. So what are the numbers here? First of all, the heat capacity, that number doesn't look very high. It's 1 calorie per gram per degree centigrade. So you'd think, one's not very big. Well, 1 is easy to remember. And it's 1 because when they set up the metric system, they used this heat characteristic of water to set this particular value. So to raise 1 gram of water 1 degree centigrade, it takes 1 calorie. They did that on purpose when they created this system. What's important is to go down here in the lower right-hand corner. This is a table from your book. For comparison, what is the heat capacity of some other substances? Well, you can see granite, which is rock, has a heat capacity of 0.2, which means that if you add a calorie of heat to some granite, 1 calorie of heat will raise that 1 gram of granite 5 degrees centigrade. Water, given the same amount of energy, will only go up 1 degree centigrade. That is a significant difference in temperature. How do you experience that? Well, think about what it's like when you go to the beach on a sunny summer day. The sun's light is energy. It is shining on the sand. And if you walk on the dry sand, by noon, that sand has a high temperature. It's going to be uncomfortable on your feet. If you go into the wet sand where there's a significant quantity of water, the sand feels much cooler. It has a much lower temperature. Now, all that sand is getting the same amount of energy from the sun, but the wet sand, because of the presence of water, the temperature is going up much more slowly than the temperature of the dry sand, which is much more efficient in turning that light energy into an increase in temperature. So that's why this is important. The next factor we want to look at here is our latent heat of fusion. And this is the amount of heat that it takes to melt an ice cube. If you have a 1 gram ice cube, it takes 80 calories of heat energy to turn that ice cube into water. If you have 1 gram of liquid water, this latent heat of vaporization tells us it takes 540 calories of energy to turn that gram of water, liquid water, into water vapor or a gas. If you think about it, that is a really large quantity of energy. That means that water vapor carries that energy with it. We get the energy back when the water vapor turns into liquid. So when water vapor turns into a drop of water, it releases that 540 calories per gram. When liquid water turns into ice, in order to do that, you have to take 80 calories per gram away from that liquid water to get that change in state to occur. So the water absorbs the energy from the sun, the atmosphere, different surfaces like your skin. Think about it. When you sweat, the water on your skin turns into water vapor, which is a gas. And when it does that, look at all the energy it's taking with it, 540 calories per gram. This is a great way to cool off, is for you to sweat. And so the water stores that energy as it goes up. And when it comes back down, it releases it. So there's this wonderful diagram in your book that kind of shows you how this works. You take your ice, you add the calories, you get the ice to turn into water. You have to add a bunch more calories to get it to up to 100 degrees centigrade. And then you add a whole bunch more calories in order to turn it into vapor. And when it condenses, it releases the heat. When the water cools down, it releases more heat. And when it turns into ice, it releases even more heat. So what this diagram is showing you is water absorbing heat energy, well, and actually just any kind of energy. So it can be light energy, which is super important because that's the energy we get from the sun. And then it can release this energy, and when it releases it, it does release it as heat, and that helps warm the atmosphere and warm other places on the surface of the earth. So there's a nice little graph in your book that kind of shows you how that works on a little line graph. And then the important heat characteristics are shown on this slide. As we've mentioned, the water stores and transfers energy. This is going to power the weather, and it's going to moderate the temperature because the temperature is not going to be able to rise and fall by huge amounts because the water that's present in the atmosphere will absorb or release heat and kind of offset what otherwise might be a dramatic change in temperature. And so that's what this slide is about. It kind of mentions it in the book, but how it moderates the global temperature. And it helps heat move from the tropics to the pole.